Imagine driving along a road positioned at nearly twice the height of the Eiffel Tower, so high that you literally pass through the clouds. That is the sensation of crossing the Huajiang Bridge, a structure inaugurated in September 2025 that quickly became a new global symbol by setting the record as the highest bridge in the world. With its deck located at an elevation of about 2,050 feet above the waters of the Huajiang River. But it is not just its impressive height that makes it remarkable, because the Huajiang Bridge challenged engineers by stretching across one of the most dangerous canyons in western China, where harsh terrain and dense layers of fog forced many previous projects to be abandoned long before actual construction even began, showing how an ambitious idea can collide with the hostile reality of nature. However, what makes the Huajiang Bridge even more extraordinary is that, right at the top of one of its towers, a glowing cafe was built among the clouds, something that looks like it came straight out of a science fiction novel, yet is completely real and open to visitors. In this video, join us as we explore how Chinese engineers turned this bold plan into a concrete reality. But before we begin, don't forget to like and subscribe to our channel. The origin of this record-breaking bridge is impressive. In fact, it all began in one of the most inhospitable regions in all of China, Guizhou Province, famous for its rugged landscape, where more than 92% of the territory is made up of high mountains and plateaus. Between them run 8 major rivers, along with countless tributaries that carve deep valleys, turning transportation and trade into a constant challenge that limited development for decades. That is why, to build the Liupanshui-Anlong Expressway, which connects the districts of Liupanshui and Anlong, the route had to cross the dangerous Huajiang River crossing inside the Great Huajiang Canyon. And that is how the Huajiang Bridge was born. A structure whose value goes far beyond a simple overpass, because it represents a milestone in regional connectivity. During the preliminary study phase, engineers faced 2 alternatives with similar costs. One was to design a gentler access road but place the bridge closer to the top of the mountain, which meant dealing with extreme slopes and landslide risks. The other option was to place the bridge lower, but extend it across a series of steep hillsides and long tunnels that would require massive excavation and cause greater environmental impact. In the end, they chose the challenge of approximately 2,050 feet in height, a decision that balanced efficiency and boldness. However, the B-shaped form of the canyon created a distance of more than 4,600 feet between the edges of the cliffs, an opening that put any conventional design to the test. At that scale, all other types of bridges failed. The tallest rigid beam bridge in the world could not span that distance without collapsing under its own weight. The longest existing arch came nowhere close because of material limitations, and even the largest cable-stayed bridge did not have the capacity to cross the gap without compromising stability. Only a suspension bridge with an ultra-long mainspan could meet these extremely demanding engineering requirements, showing how every solution solves one problem but creates another in the chain of technical decisions. So how do you build a colossal bridge in such an unforgiving landscape? In principle, there are 3 fundamental stages. First, erect the 2 main towers. Then, stretch the 2 main cables and anchor them firmly. And finally, hang the bridge deck using the vertical hangers. But that is just the basic theory. In practice, everything becomes much more complex because of the site's unique conditions. The Huajiang Bridge rises about 2,050 feet above the river, with a span of 4,660 feet crossing the canyon. And when the tower structures are included, the total height rivals that of the tallest man-made building on Earth, the Burj Khalifa. Even in a far more hostile natural environment, with such gigantic dimensions, it becomes clear that the Huajiang Bridge is not just huge on paper. It requires a construction process that goes far beyond standard infrastructure practices, incorporating innovations in materials and techniques to deal with wind, seismic activity, and erosion. Beyond the obstacles of the terrain, the foundation of the structure presented another complex dilemma. The tower foundations had to be drilled deep into altered rock layers full of cracks and groundwater, where the smallest mistake could cause serious accidents, such as collapses or flooding during excavation. Because of this, engineers used a special pile system, driving 24 massive concrete piles into the ground, combined with earthquake-resistant steel reinforcement to ensure the towers could withstand decades of operation under dynamic LOA design approach that integrated computer modeling to predict geological behavior. After overcoming the foundation challenges, the next step was to raise the 2 backbone columns of the entire bridge. The main towers, one 860 feet tall and the other 673 feet tall, act as the anchoring points for the entire cable system. They were erected directly on the mountain slopes, hundreds of feet above the abyss, along with the 2 giant cables that each weigh more than 19.8 million pounds, made from imported high-strength steel treated to withstand extreme tension. These towers support the bridge like 2 colossal pillars holding a ribbon suspended in the air, and their stability is vital. That is why the entire structure is reinforced with high-toughness steel capable of withstanding strong winds. traffic-induced vibrations, and even earthquakes over its projected service life of more than a century, incorporating seismic dampers based on energy dissipation technology. But for these massive towers to fully perform their function, the cable anchoring system at both ends of the bridge had to be strong enough to hold the entire structure in place, preventing any displacement. The Huajiang Bridge anchorages act like giant counterweights that firmly secure the two main cables into the mountains, using the local geology to their advantage. On the Shenfeng side, the gravity-type anchorage sits solidly on the slope, with a total concrete volume of up to 214,500 cubic yards, forming an extremely stable resistance block that distributes the tensile forces. On the Wanling side, the anchorage was designed as an anchoring tunnel, an ingenious solution in which, instead of placing a massive block on the surface, engineers excavated deep into the mountain and connected the system directly to the natural rock, transferring all cable tension into the rock mass itself, minimizing visual impact and maximizing integration with the environment. The reason for this choice was clear. Behind the tower, on the Wanling side, there is a steep mountain, but the amount of flat land available is extremely limited, which made a surface anchorage impractical. So using the mountain itself as a natural anchor became the ideal option, saving space while increasing the stability of the entire structural system, and also allowing for a more environmentally friendly construction by reducing material extraction. After completing the anchorage blocks, the next step was to install the temporary catwalk, a suspended walkway between the two towers where workers would assemble the entire cable system, a process that required millimeter-level precision to avoid dangerous oscillations. To launch the first guideline across the canyon, which is hundreds of feet deep, engineers used drones equipped with global positioning technology, making cable guiding safer and more precise than traditional methods using helicopters or manual launches. Once the guideline successfully crossed, the temporary catwalk was formed, establishing the base for the most critical phase, building the two giant main cables of the bridge, which function as the backbone of the entire structure. Each main cable is made up of tens of thousands of high-strength steel wires woven together with absolute precision to create a structure capable of supporting tens of thousands of tons of load, including traffic, weight, and environmental forces. On the suspended catwalk, workers installed each wire bundle, with each bundle consisting of 91 high-toughness steel wires measuring about 0.22 inches in diameter, pulled back and forth between the anchorage points under GPS supervision to keep the error below 0.08 inches, a tolerance that ensures uniformity even under strong winds and hundreds of feet above the ground. Controlling every movement of the bundles was essential to avoid tangles or irregularities that could compromise structural integrity. After all, 217 bundles were installed. A compaction machine compressed and united them into a circular cable through a specialized compaction process, after which the cable was wrapped in several protective layers to resist corrosion, harsh weather, and vibration for decades, including galvanized coatings and epoxy paints. Only when these two giant cables were finished could the bridge move on to the next stage, suspending the deck in the air, a moment that marks the transition from a skeletal structure to a functional roadway. First, engineers installed the system of vertical hangers, each attached to the main cable through specialized clamps capable of withstanding thousands of tons of force. Designed with fatigue-resistant alloys, these hangers transfer the load of the bridge deck to the main cables and then distribute it to the two anchorage points, creating a dynamic balance that adjusts to thermal changes and load variations. After that, the entire bridge deck girder, made up of 93 steel segments, was assembled piece by piece, starting from the center of the bridge and gradually extending to both sides, a symmetrical method that minimizes uneven stresses. Each segment, weighing hundreds of tons and manufactured in remote workshops with precision welding, was lifted using a pulley system, suspended more than 2,000 feet above the water, and connected to the hangers through specialized load-bearing joints that allow controlled movement. During installation, engineers constantly adjusted the cable sag, the tension in the hangers, and the position of each panel to ensure that the entire deck remained aligned, without tilting or twisting under wind forces, using real-time modeling software for predictions. Once all 93 segments were in place and joined into a single structure, the upper roadway was built, transforming the suspended steel skeleton into a fully operational expressway, with wide lanes, safety barriers, and drainage systems designed to handle heavy rainfall. After construction was completed, the next step was to evaluate the bridge's real strength through rigorous testing. In the load test carried out in August 2025, 96 heavy trucks, with a total weight of about 16 million pounds, were used to measure load capacity and dynamic behavior, simulating maximum traffic and extreme conditions. More than 400 sensors recorded data on deformation, stress, and vibration, ensuring that the bridge met the strictest safety standards established by international regulations, such as those of AASHTO, adapted for China. This test not only confirmed its absolute safety, but also demonstrated advances in real-time structural monitoring, with IoT systems that detect anomalies early for predictive maintenance, extending its service life. The Huajiang Bridge is not just a colossal engineering structure, but the result of the ingenuity, effort, and determination of Chinese engineers who overcame barriers that once seemed insurmountable. From the earliest days drilling deep into the rock layer, pouring concrete for the main tower shafts, to completing the tower tops, installing the transverse steel beams, tensioning the suspension cables, and adjusting every final component with micrometer-level tolerances. Each stage was filled with challenges and required absolute precision, incorporating 3D simulations and wind tunnel tests to anticipate problems. Looking back at the entire process, the bridge seemed to grow day after day, going from being just an idea on blueprints to becoming a majestic reality crossing the deep canyon. It is a testament to how China has led the construction of super-high bridges, going from having only one above 400 feet in 1994 to dozens today, breaking records such as the former 1,850-foot record of the Baipanjiang Bridge. Throughout the construction of the world's highest bridge, the team constantly faced extreme challenges from both nature and terrain, which tested their endurance every day. The Great Huajiang Canyon is known for its strong winds, which in certain seasons can reach level 14 on the Beaufort scale, while work had to be stopped whenever winds reached level 6 or higher, to protect workers' safety, as they operated with safety harnesses and strict protocols. When transporting steel beams into installation position, stabilizing ropes sometimes twisted due to unpredictable gusts, forcing workers to straighten them manually and balance the lines between upstream and downstream sides to reduce the risk of twisting, a process that required team coordination under pressure. They began work at 6 a.m. and often returned only after nightfall, working extended shifts in cold and high humidity conditions. In addition to wind and rugged terrain, the enormous volume of construction materials also represented a major obstacle, because the Huajiang Bridge required a total of about 15.5 million cubic feet of concrete, equivalent to 176 Olympic swimming pools, transported along narrow and exposed roads. To reduce costs and protect the environment, engineers reused the leftover rock generated during excavations, crushing it into high-performance green mineral powder and using this material as a supplement to replace 20% of the cement in each cubic foot of concrete, a technique that not only saved cement and reduced expenses, but also made full use of waste, limiting pollution and preserving natural resources such as quarries. Thanks to these innovative measures, the team not only overcame natural and geographic challenges, but also completed the project in a sustainable and efficient way, integrating ecological practices such as using solar energy at construction sites and minimizing emissions. After all the effort to conquer mountains and cliffs, the bridge now opens a completely new world for this remote region. In the past, traveling from the bridge area to the city of Wanling took at least 3 hours on winding and dangerous roads. Now, this time has been reduced to at most an hour and a half, saving almost half the time and reducing traffic accidents. Faster travel not only makes daily life easier for local residents, but also benefits thousands of people in the region by improving access to markets, services, and opportunities. As a transportation project integrated with tourism, the Huajiang Bridge was planned from the beginning to ensure both structural integrity and visitor experience, attracting adventurers and tourists. With wide views, ideal height, and beautiful scenery, both sides of the bridge were equipped with reinforced guardrails and a special pavement coating that not only stabilizes the deck, but also supports high-altitude adventure sports such as guided walks. Inside the steel girder there is a visitor corridor that, if not for tourism, would serve only as a maintenance path, but now offers panoramic views with information panels about the construction and its impact, which goes far beyond what is visible. By connecting to the G56 expressway, the bridge not only reduces travel times, but also opens regional trade routes between China and Southeast Asia, attracting investment, creating jobs in sectors such as logistics and hospitality, improving education and healthcare through better access, and boosting tourism with attractions like the bungee jump platform, pushing the entire region toward a prosperous future. The Huajiang Bridge is not just a gigantic engineering structure, but the result of the ingenuity, effort, and perseverance of Chinese engineers who overcame barriers once considered insurmountable. From the earliest days drilling deep into the rock layer, pouring concrete for the main tower shafts, to completing the tower tops, installing the transverse steel beams, tensioning the suspension cables, and adjusting every final component with micrometer-level tolerances. Each stage was filled with challenges, incorporating 3D simulations and wind tunnel tests to anticipate problems. Looking at the whole process, the bridge seemed to grow day after day, going from being just an idea in design plans to becoming a majestic reality crossing the deep canyon, a testament to how China has led the construction of super-high bridges. going from just one above 400 feet in the last century to dozens today, breaking records such as the former 1,850-foot mark of the Baipanjiang Bridge. The story of the Huajiang Bridge is not just that of a world record, but an example of the transformation of Guizhou province from an isolated and rugged territory into one integrated with the modern rhythm of the 21st century, with an economic impact estimated in millions of dollars in annual tourism. Stay with us as we continue exploring more mechanical wonders and technological advances around the world. Subscribe so you don't miss what's next. See you next time.